A quick reminder, this is section 6.4, working with Taylor series. 1 plus b raised to the 0 power, anything to the 0 power is 1. A plus b raised to the 1 power is a plus b. A plus b squared is a squared plus 2ab plus b squared. Somebody paid attention to the numbers. This is called Pascal's triangle. Somebody said, look, we can make a prediction of how things work, and this was used for the longest time. They said, if you're looking at a plus b to the 6, you start with the first one being raised to the 6th power, then lose 1, b must pick that up. The degree of each term should be a 6. Then lose 1 term, that's a to the 4th. That has to be b squared because those must add up to 6. 3, 3. 2, 4. 1, 5. And b to the 6. Now, the issue, that was the easy part. The hard part was the coefficients. And this is how they figured the coefficients. Pascal figured out how to do this by using the following triangle. Said, look, take 1 plus 1, that's 2. 1 plus 2 is 3, 1 plus 2 is 3. And that's where the 1, 3, 3, 1 come from. If you're dealing with the 4th, 1 plus 3 is 4. 3 plus 3 is 6, and 1 plus 3 is 4. 4, 6, 4. 1 plus 4 is 5, a 10, a 10, and a 6, and a 5. 5, 10, 10, and 5. So if they wanted to figure this out, they said, look, that's a 6, that's a 15, that's a 20, that's a 15, that's a 6, that's a 1, and that's a 1. And that's how it was done. The issue with it was, if you wanted to find a plus b raised to the 20th, you need to list the first 19 rows of this pyramid. Later on, they discovered the binomial theorem, which is identical. You're still taking a plus b, let's say, to the 6th power. They said that's 1 times a to the 6. And then, the way it works, a to the 5th, b to the 1, a to the 4th, b squared, and the list goes on. And what they figured out that, look, n choose 0 for the first, and choose 1 for the second, where n choose k is n over k factorial times n minus k factorial. An easy way to remember that is to say, look, if this is a 5, this is a 5 factorial, 1 factorial. If this is a 4, that's 4 factorial, and that's 2 factorial. And that's an easy way of remembering that. Now, the reason we're talking about those, because we're trying to figure out the Maclaurin, specifically Maclaurin series for 1 plus x to the k, which kind of looks like that. So if I wanted to use the Maclaurin series, I'm going to try and use brute force, and I'm going to figure out that, wait a minute, that is f of 0, f prime of 0, x to the 1 over 1 factorial, plus f double prime of 0, x squared over 2 factorial, triple prime of 0, x cubed over 3 factorial, and the list goes on. And I go on the side, I say, okay, f equal 1 plus x to the k. At x equals 0, that is simply 1. 1 to the k is 1. The derivative is k into 1 plus x to the k minus 1. Let x equal 0, k times 1 raised to a power is 1. F double prime is k times k minus 1. 1 plus x 1 plus x to the k minus 2. Put 1 in there, you get k times k minus 1, and maybe one more. The third derivative will be k into k minus 1 into k minus 2, 1 plus x to the k minus 3. And if you put 1 in there, you get k into k minus 1 into k minus 2. So this becomes 1 plus x to the k becomes 1 plus, and this is kx to the 1 over 1 factorial. This is k times k minus 1 x squared over 2 factorial plus k into k minus 1 into k minus 2. And the list goes on. Now, no need to do any of that. If we're talking about any form that looks like this, the formula in the book stops right there. What that means, you could use this straight. This is called binomial series. Binomial series deals with any form of 1 plus x raised to a power. And it's using this formula really because of these terms, but that's a lot of work if you're going to go about it and derive it from scratch. So we're going to jump straight to it. Now, on your final exam, you're provided the following table. And if you are in Pasadena City College, you're provided the following table. It's a slightly different table. Let me see where it is. And the formula given to you looks like this. Right there, binomial. So you're given you're given 1 over 1 minus x, you're given e to the x, sine of x, cosine of x, natural log, and 1 plus x to the k, and you can see it right there. That's Pasadena. But if you're at Cal Poly, the department is going to give you that. You need to know that this right here, instead of writing this right here, this is simply this is simply going to be 1 plus kx to the 1 over 1 factorial, k times k minus 1 x squared over 2 factorial, and the list goes on. Now, I'll ask in the department if they allow us to do that at Cal Poly, but for Pasadena, you're going to be given that. So we're just going to use it. No need in going right there. Look at that. This is right there automatically. All what you have to do is write it in the right form, meaning write it in the form of 1 plus a quantity raised to the k. Make sure that is a 1. Make sure that's a plus. Identify what is x and identify what is k. And then automatically that is 1 plus kx plus k times k minus 1 x squared over 2 factorial. That is x. I messed up. 1 plus kx to the 1 over 1 factorial plus k, subtract 1, subtract 1, and the list goes on. So when I'm looking at a problem like this, now here they tell us that, look, suppose that this is given. I could derive that when there's a need, and I'm going to need to do that. When I'm integrating 0 to x, I'll say, okay, that is, instead of this, again, they gave me this formula. For now, they're allowing me to use it. That is 1. So the only thing what you have to do is replace x by t. So here they're stopping right there. They're only using the 5th degree polynomial. You know by now how that works. And what would that be? dt. that would be t minus t squared over 4 minus t cubed over 24 minus t to the 4th over 64 minus 5t to the 5th over 5 times 128, the 5's cancel out, minus 7t to the 6th over 6 times 256. I'll figure out what that is in a minute, evaluated from 0 to x. And that would simply be x minus x squared over 4 minus x cubed over 24 minus x to the 4th over 64 minus x to the 5th over 128 minus 7x to the 6th over, what is that, 36, 30, 33, 12, 15, 36. There it is, done deal. No problem there. So any form that looks like this, they say, look, 1 plus x to the 1/3 is given by this. Very good. There's x right there. There's x right there. And the 1/3 matches. Very good. The only thing that's varying is this part. So what do you think that's going to be? That is going to equal 1 plus 1/3. In place of x, you're going to put in 4x minus 1 over 9 4x squared plus 5 over 81 4x cubed minus 10 over 243 4x to the 4th. Now this is the first time I see, this is the first book that simply gives you the actual equation. Normally you have to derive it yourself. Normally you come in and say, look, 1 plus x to the 1/3 is going to be 1 plus kx to the 1 over 1 factorial, k times k minus 1x squared over 2 factorial, k times k minus 1x times k minus 2x cubed over 3 factorial. And you figure out what those are. That's 1 plus k is 1/3. 1/3 times, now 1/3 minus 1 is negative 2/3. 1/3 minus 1 minus 2. And that's how you come up with all of these equations. You know, that is 1 plus 1 over 3x to the 1 minus 2 over 9. The 2's cancel out. Minus 1 over 9x squared. And here you notice that this is going to be, this is 3 times 2 times 1, so the 2's cancel out. That is a 5 over 3 times 3 times 3 times 3, 81. And that's where this comes from. And then replace x by 4x. But here they give you that. No big deal. But just, you know, they like us to do things the easier way, not an issue. 4x over 3 minus 16 over 9x squared plus 4 cubed, 64 times 5, 64 times 5, that is 320 over 81 x cubed minus 60, what is that for? 16 times 256, add a 0, and then it goes on. And there it is. Normally you have to find a power series representation for this. You have to write this as a summation. This author doesn't really care much for that, so we're going to do the same. And here, if I wanted to match again, given this, if I told you what this is, and I said here, given that, can you find what this looked like? Okay, well, let's see how that works. They want it centered at -1. All what you have to do is make it look like what they gave me, except instead of x, it's x plus 1. So I start by taking the 1 out, and that will be 2 plus 2x to the 1/3. That is 1 plus 2 into x plus 1 all raised to the 1/3. And now I could say, look, that's taking the place of my x, that's taking the place of my k. So if I copy down what's up there, well, that is 1 plus, and again, I'm just copying literally what they gave me. Oh, I used different colors. I apologize. I should have used blue and and those were right there. So here, all what I have to do, replace the blue part with 2 into x and replace there. So I'm really looking at 1 plus 1/3, and instead of x, it's 2 into x plus 1 to the 1 over 1 factorial, plus it minus, it was 1 over 9, and the x, it's going to be 2 to x plus 1 squared over 2 factorial, plus 5. Oh, I'm sorry. I'm just copying. I'm not deriving. I keep on forgetting that. So basically that right there, 1 over 3, it's going to be plus 5 over 18 times, and instead of x, it's going to be 2 into x plus 1 cubed. And then after that, we are looking at minus 10 over 243 into 2 into x plus 1 to the 4th. And the list goes on. And I would simply say, look, 3 plus 2x raised to the 1/3 is going to be 1 plus 2/3 x plus 1 minus 4/9 x plus 1 squared plus that is 2, that's 8 divided by 2, that's a 9, there's a 4, that's 20, 8 let me see. I have something else in my notes. That's not an 18, that is 81. That's my mistake. I apologize. I'm so sorry. So that is 40 over 81x plus 1 cubed minus, this is 2 to the 4th. 2 to the 4th, that's 16 times 160, 243x plus 1 to the 4th, and that is goes on. Again, the hard part is writing this as a power series representation. You're not required to do that. And then they say, look, if this is what you're given, can you use that to evaluate 2 to the 1/3? You say, yeah, I could. That's 1 plus 1 to the 1/3, right? Replace x by 1 and you're in very good shape. That is 1 plus 1/3 times 1 minus 1/9 times 1 squared plus 5 over 81 times 1 cubed minus 10 over 243 times 1 to the 4th, and the list goes on. That turns out to be 1 plus 1/3 minus 1/9 plus 5 over 81 minus 10 over 243, right? And that is approximately 1.242798353. In reality, if I take the cube root of 2, that turns out to be 1.259925, so this is accurate to 1 decimal place. And the reason for that, because cube roots are slow growing. Now, anytime you see in the book them saying find the Maclaurin series, you could use the following table. Anytime they say use the Maclaurin series, let me see. Okay, let me make that 2 videos. This way I'm not gonna try to rush and cram things up. And here we are. Anytime they say find the Maclaurin series, these are the Maclaurin series. That means you could use the table. Well, we want to find a Maclaurin series for f of x equal x e to the x, e to the 2x. We know that e to the x all of these are dependent on x. So what does that mean? That means I could say, look, e to the 2x is the series n equals 0 to infinity. In place of x, replace 2x to the n over n factorial. That is the series n equals 0 to infinity, 2 to the n over n factorial x to the n. Now, if I multiply that by x, I'll get x e to the 2x equal the series n equals 0 to infinity, 2 to the n over n factorial x to the n plus 1. Now, the author sometimes accepts that. In general, if you can fix that to be x to the n, you must. So I'm going to shift this 1 power down, shift this 1 power down, shift this 1 power down. To compensate, shift this 1 power up. Both of those are accepted on the exam, but this author accepts both. That's really what's accepted normally in most applications. If you can make it x to the n power, you should. Well, here we have another one. We're dealing with the sine of x. From this table, we know that the sine of x is the series n equals 0 to infinity, negative 1 to the n, x to the 2n plus 1 divided by 2n plus 1 factorial. So, if I take this and I multiply it by 1 over x, I would say the sine of x over x is the series n equals 0 to infinity. Nothing's going to be affected as far as coefficients. The only value that's going to be affected, you're going to subtract these powers, and that's going to be 2n plus 1 minus 1, which is 2n. And since that's cannot be made an n, because it's not shifted left or right, then you leave it alone, and that's pretty much the answer. Now, you could list them out if you want. You could say, okay, look, n equal 0. That is 1 minus, let n equal 1, x squared over 3 factorial plus 2 over 5 factorial minus x. Again, normally you would need to know both. I'm listing those for you. Anything I box is the answer. That's the one that they want. But in reality, that's what you use in applications. If you're going to take discrete math, or that's how you would see it. Sine of x squared, we just did the sine of x. We just said, look, the sine of x was the series n equal sine of x was the series n equals 0 to infinity, negative 1 to the n. It was x to the 2n plus 1 divided by 2n plus 1 factorial. If I'm not mistaken, that's the odds. There it is. Okay, very good. So what do you suppose the sine of x squared is? Well, that is the series n equals 0 to infinity, negative 1 to the n. And I'm going to replace, in place of x, x squared. Everything else is going to remain the same except for that x. And what do you think that becomes? Clean it up and you're set. That is the series n equals 0 to infinity, negative 1 to the n, x to the 4n plus 2 divided by 2n plus 1 factorial. Now, I could shift this, but since there's no way of making that x to the n, there it is. And if I wanted to list a few of the terms, n equals 0 will give you x squared minus n equal 1 will give you x to the 6 over 3 factorial, x to the 10, 8, yeah, over 5 factorial. Again, you should know both of those. That's the point of you writing this, but that's the answer in the back of the book, and that's what you should do. The author seems to like the summation. You're responsible to know both when the time comes. This problem right here, cosine of x squared, we have a problem. Why is that? Because if you're going to square both sides, squaring an infinite amount of terms is highly not recommended. That's a big deal, big issue. Instead, we say, look, cosine squared is 1/2 plus 1/2 times the series n equals 0 to infinity. And now I'm using this with one minor change. I'm replacing x by 2x to the 2n. And then cleaning that up and seeing how that plays. That is 1/2 plus 1/2 the series n equals 0 to infinity, negative 1 to the n, 2 to the 2n over 2n factorial, x to the 2n. That's a fine answer. If you notice, if you let n equal 0, you don't have to do this part. If you let n equal 0, or actually, yeah, if you let n equal 0, n equals 0 will give you a 1 times 1 times 1 over 1 plus the series n equal 1 to infinity of negative 1 to the n, 2 to the 2n, x to the 2n over 2n factorial. And of course, that gives you a 1 plus that series right there. And now, if you let n equal 0, that includes that 1. Notice if I let n equal 0, I'll get exactly that, but you're not responsible to do all of that work. This is a fine answer right there. Once you get the summation, it's all good. No need to really take it any further. And here we are. Suppose I want to integrate this, and here it says specifically, find the Maclaurin series for this integral. So using the Maclaurin series, f of x is the integral from 0 to x of e to the negative t squared dt. That is the integral from 0 to x, the series n equals 0 to infinity, negative 1 to the n, t to the 2n divided by n factorial dt. That is the series n equals 0 to infinity that should be c plus, oh, it's a definite integral, never mind. That would be the series n equals 0 to infinity, negative 1 to the n over n factorial t to the 2n plus 1 divided by 2n plus 1. Evaluated from 0 to x, put x in there, that's the series n equals 0 to infinity, negative 1 to the n over n factorial times 2n plus 1 times x to the 2n plus 1, and if you put 0 you get 0, and that's pretty much the final answer, and that concludes this section.